evaluate a triple integration easily, we must have to transfer our coordinate system from Cartesian to spherical. Okay. Now in this class we discuss what is the spherical coordinate system and how can take the range of the spherical coordinate system in triple integration. Right. Now it is clear that in triple integration, that is the integration in 3 dimensions. So there must be 3 axes in Cartesian coordinate which are x, y and z. We first draw 3 axes of coordinate. Let this be z axis, this be x axis and this be y axis. Okay, this is x axis, this is z axis and this is y axis. And let any point P we draw here, but this is lies on the space. The coordinate of P, this is x, y, z. And in spherical coordinate system, this is denoted by r, theta and phi. Now we clear what is r, what is theta and what is phi. Okay. Now we project this point P xyz in xy plane, right? Then the projection of this point in xy plane is this is P dash and it be x, y and this is 0. Okay, because P dash this is equal to z. Here P dash this is equal to z. Okay, and we draw a radius vector from the origin to the initial point P. This is O origin, this is the initial point P. Okay, and this is the radius vector r of the spherical coordinate system R. Right. So the length r is OP. Here r this is equal to OP. Okay. Now the angle between OP and OZ, this is taken to be theta in this spherical coordinate system. And since we project the point at P dash on xy plane, so we see that this is OP dash. Okay, and here triangle OP dash P, OP dash P is a right angle triangle. Okay, and for this right angle triangle OP dash P, this angle is theta. This is alternate angle or vertically alternate angle. Okay, and this is pi by 2. Here we draw a picture of 3-dimensional space in 2 dimensions. So originally this is not look like pi by 2, that is not like right angle, but it is taken to be right angle because we draw from this point to this point. This is perpendicular to xy plane. Okay, so this is perpendicular. And from the property of right angle triangle, we see that this is the base and this is the height. Okay, so we write here this is r sin theta and this is r cos theta. Okay, this is the base and this is the height. Now if we draw a line perpendicular to z axis, okay, from the point P, and this is given by like this. Okay, and here we take a point, this is taken as Q and this is on the y axis and the coordinate of Q is 0, y 0. Clear? And this must be also a perpendicular, because this is perpendicular on y-axis, and we know that this is x and this is y. From this triangle OQP dash, here this angle is taken to be phi in the spherical coordinate system. Now since this is the angle phi and this is perpendicular, that is the right angle, so this is base and this is perpendicular, or this is the height of the right angle triangle OQP dash. Sorry, this is P dash. Okay, so we get here, this is the hypotenuse of the right angle triangle and this is the angle. So we get here x, this is equal to r sin theta into sin phi. Okay, this is r sin theta sin phi, and the base y, this is r sin theta cos phi. Okay, if we draw a perpendicular from P to the z axis, this is r sin theta, because this is equal to OP dash. Okay, OP dash, and T, if we name this point as M, then PM, this is equal to OP dash. Right. So the spherical coordinate system of XYZ is becomes x, this is equal to, we get here r sin theta sin phi, y, this is equal to r sin theta cos phi, and z, this is equal to r cos theta. And these are the transformation from Cartesian coordinate system to spherical coordinate system. We can also draw a perpendicular from P dash to the x-axis. Let it be Q dash. Then P dash Q is also y, and this is also r sin theta cos phi. Okay, it can be done here. Now if we take, or if we change the coordinate system from Cartesian to spherical, then how can we take the range of the integration? That is, what are the range of r, what are the range of theta, and what are the range of phi? Okay, we discuss the case one by one. The first case, if we take the complete sphere, okay, complete sphere like this, x square plus y square plus z square, this is equal to a square, and clearly it is shown that the radius of the sphere is a. So we get, for the complete sphere, the range of r is 0 less equal to r less equal to a. Okay, and for the complete sphere we take the range of theta and range of phi. Yes, for the complete sphere we take the range of phi, this is equal to 0 to 2 pi, a complete revolution of phi in xy plane, right? This is 0 to 2 pi, and we take the range of theta from 0 to pi. Okay, when theta is completely revolved 360 degree, and if phi is revolved 360 degree and theta is revolved from 0 to pi, then we get the complete sphere. Okay, now for the second case, that is a hemisphere. The first range is obviously same, and what about the second, and what about the third? For the hemisphere, it is clear that hemisphere is lies above the xy plane. Okay, above the xy plane. So here only change, theta is from 0 to pi by 2, and phi is the same, this is from 0 to 2 pi. That is, we take the hemispherical bowl. We must take the base of the hemisphere. This is a complete circle on xy plane. So we get phi from 0 to 2 pi, but theta from 0 to pi by 2. Because if we take theta from 0 to pi by 2, then we get the complete hemisphere on above of xy plane. And for the third case, a octane of or positive octane, okay, positive octane. Then the range are 0 less equal to r less equal to a. This is the first range. This is unaltered. And here the range of theta and range of phi both are 0 to pi by 2, 0 to pi by 2. Because for the first octane, that is OX, OY, and OZ, we have to take the value of phi from 0 to pi by 2, value of theta from 0 to pi by 2, and value of r, this is from 0 to a. Clear? Now to change the coordinate system, we must find out the Jacobian of this system. Okay? And if we determine the Jacobian of the system, that is del of x, y, z to del of r, theta, phi. And we know that this is the determinant del x by del r, del x by del theta, del x by del phi. And similarly we get del y by del z pi. This is 3 cross 3 determinant, and if we put all the value of the partial derivative here and we expand this determinant, we get the Jacobian as r square sin theta. Okay, so by transforming the coordinate system to Cartesian to spherical coordinate system, we can write, or we must write, dx, dy, dz. This is the elementary volume in Cartesian coordinate system, and we write here r square sin theta dr, d theta, and d phi. This is the elementary volume in spherical coordinate system, and this is the elementary volume in Cartesian coordinate system. This is dv. Okay, this is the transformation from Cartesian to coordinate, and this is the range for different case of spherical coordinate system, and this is the actual method of spherical coordinate system. Okay, thank you for watching.